Hi there. Today, me and my associates will walk you through how our software conducts torsional analysis of a cylinder shaft that you will be using for your models. Torque is defined as a force that acts perpendicular on a shaft at a certain distance away. Internal torsion is defined as a moment that tends to twist a member about its longitudinal axis. The main applications that take torsional analysis into account are used in the design of drive shafts in vehicles and machinery. As the torque is applied in a twisting fashion on a shaft, an angle is formed based on circumferential movement along the direction of rotation. Taking a cylindrical cross-section of the rod, when a torque is applied, the front face of the rod faces a different amount of torque as compared to the back face. The back face experiences only the deformation caused by the circumferential rotation. The front face, however, experiences circumferential rotation along with the change in angle for that circumference as well. The difference between the rotational forces on the front face and the back face causes the rod to experience shear strain. Since the change in angle and the change in the radial distance are the same amount for a given radial distance, they can be taken as a linear constant. This indicates that the shear strain at any distance from the neutral axis on the rod depends on the maximum shear that the rod undergoes at the outer boundaries multiplied by the radial distance of rotation and the maximum radius of the shaft. If the given material of the shaft is linear elastic, then a relationship using Hooke's law can be used to develop a relationship between the shear strain to find the shear stress that the shaft undergoes due to the torque applied. Thus, a similar equation for the stress can be used. As we said earlier, torque is mathematically known as a force being applied perpendicularly at a certain distance away. Torsion is therefore dependent on the stress applied over the area that it is concentrated over. Here, the max stress and the radius of the rod is a constant, so the integral to find the torque depends only on the radial distance of the shaft and the change in the area at that radial distance that we choose to specify. We can collect these like terms and call them J to simplify the formula, so it can be seen as the following. These are commonly referred to as the torsion formula, which will be how the software will calculate the torsion for your models. J is referred to as the polar moment of inertia and can be calculated using a differential ring moving outwards from the neutral axis if the shaft is solid. Taking its integral, we can see that the polar moment depends on the radius of the rod. If the rod has a hole in the middle, then the moment depends on the outer and inner radius of the shaft respectively. Thus, we can see that the stress at any given point varies linearly with the radial distance, and the internal torque therefore also forms a linear distribution along the radial distance of the rod. Stress can be visualized increasing as we move towards the edge of the pipe. At small distances of x into the pipe, the stress distribution follows the same pattern and applies to the adjacent faces as seen on the picture as well. Once the maximum shear stress has been overcome, a crack will form along the longitudinal axis of the rod and cut right through towards the center of the shaft, as seen in the following picture below. Our software would show you the stress distribution that the shaft can handle throughout the entire rod, and my associate Joe will show a sample of how the software will calculate the stresses at any given point.
Hi everyone, today we're going to be doing a simple problem using the torsion formula. You can find this in section 5.2 of the Hibbler textbook. If you haven't watched the lecture slides yet, please do so before watching this video in order for you to have a full understanding of the content. So here you can already see I have steps written out. I'm just going to take you through it using this problem. So here we go. The problem states that the solid shaft and tube shown in figures 5-A are made of material having an allowable shear stress of 75 megapascals. Determine the maximum torque that can be applied to each cross-section and show the stress acting on a small element of material at point A of the shaft and points B and C of the tube. So, in order to first start this problem, we're going to start with a polar moment of inertia equation in which J equals pi over 2 times c to the power of 4, in which c is the radius. So, doing this, we're going to have pi over 2 times 0.1 to the power of 4 equals 0.1571 times 10 to the negative 3 meters to the fourth. As you can see, we did a unit conversion here, unit to meters. Now we're going to do the same thing for the tube, but we're going to be subtracting the two radiuses, or radii, in order to compute this. So we're going to have 0.1 to the power of 4, subtract 0.075 to the power of 4 times pi over 2. This results in 0.1074 times 10 to the negative 3 meters to the fourth. Alright, since we have our polar moment of inertia, now we can move to the shear stress formula, Tc over J. But we're solving for T, which is the internal torque. So we're going to have to rearrange the equation, and in doing so we get the shear stress multiplied by the polar moment of inertia over the radius, 0.1. This results into, well, here we're just going to plug in the values. We're going to have 75 times 10 to the negative 6 times 0.1571 times 10 to the negative 3, all over 0.1. The result is 118 kilonewton meters. This is the maximum internal torque of the shaft. We're going to do the same thing for the tube, rearrange the equation, input the values, and we get 80.5 kilonewton meters. Now, since we have our T value, the internal torque, we're just going to solve for the stress. So all we're going to do is plug in our values. We're going to use the lower torque here, the lower maximum torque. Put it here. We're going to have 80.5 times 10 to the 3 multiplied by 0.075, which is the internal radius, all over 0.1074 times 10 to the negative 3. This results in a shear stress of 56.2 megapascals. So as you see, this was a simple problem just displaying basic knowledge of the concept at hand. Hopefully this helped, and I will be posting more videos in the future to help you develop a full understanding of this topic. Thank you and have a good day.